Welcome to the third part of the lecture. In this part, we talk about principal stress and strengths. Let's continue with our mitral valve example. Assume that we want to design an artificial one. We've already seen that we can calculate the stress tensor for each point inside a body. For design purpose, it's beneficial to find the direction of a cubic element with surfaces perpendicular to the traction vectors at a point. The direction of this cubic element shows the principal directions at a point, and the traction vectors are called principal stress vectors, and their values are principal stress values. Here is more details. Remember the Cauchy stress formula where we had T equal the traction vector equal to the normal to this surface dot the stress tensor at the point. There we noted that a stress component on a surface are components of the surface traction vector. For example, for T of E1, meaning that the traction on a plane perpendicular to principal to a reference frame first vector, its components becomes sigma 11, sigma 12, sigma 13. Nor the stress normal to that plane and stresses parallel to that plane, normal stress and shear stresses. So we know that T is not necessarily aligned with the normal to the surface. In case of principal stresses and principal stress directions, if for a surface the traction vector is aligned with the normal to the surface, then we can say that traction is equal to sigma, a scalar, multiplied by Ni, the component of the normal vector to the surface. You see it here. So compared to the top cubic element, if we rotate that cubic element somehow, that the surfaces of this cubic element becomes perpendicular to the traction vectors on those surfaces, we end up with no shear stress on any of these surfaces, and we end up with having a cubic element with only normal stresses on its surfaces. So these normal stresses, sigmas, which are scalars, we call them principal stress values. And the normal to these surfaces are principal stress directions. And plane perpendicular to N is principal stress plane. So you see that we transformed, rotate the cubic element, and we ended up with principal stress planes with principal stress directions on which we get only normal stresses, and we call those normal stress values principal stress values. The same point, only normal stresses act on a principal plane, so there is no shear. Here is a very simple example. Note that at point P in Mr. Potato, we have two planes. The first plane, the traction vector at point P has two components, a normal to the surface and a shear to the surface. In the second case, we passed another plane through the same point, but this time the traction vector is aligned with the normal to the surface. So basically, the second case, we have a principal stress direction N, and this plane is a principal stress plane. This is how we find the principal stresses and stress directions. So, in the case of principal stress, both of these equations should satisfy. This is the general Cauchy stress equation, and this is the case that that the normal is perpendicular, is parallel to the principal stress, where sigma is a scalar. So we basically end up with a simple eigenvalue problem for a symmetric second order tensor sigma ji here. Let's expand it in the vector and notation forms. Sigma is a 2x2 tensor. Delta ji sigma is a diagonal second order tensor with all of diagonal elements to be 0, and nj is basically a column vector representing the normal vector of a plane. If I do the multiplications, I end up with these three algebraic equations to solve. This is an eigenvalue problem. So the following determinant should be 0. Just know that we change the notation order for just simplicity in reading the equation. So basically, the determinant of sigma ij minus delta ij sigma should be 0. The characteristic equation of our eigenvalue problem becomes sigma to the power of 3 minus the first invariant sigma square plus the second invariant sigma minus the third invariant equal to 0, for which we find three solutions: sigma 1, 2, 3, which are the principal stresses of the stress tensor sigma ij. So the first, second, and third invariants of the stress tensor, these are three real value scalars, meaning that they don't depend on the choice of coordinate system. For example, they're invariant to a coordinate transformation. So it doesn't matter if you rotate the coordinate system, you always get the same numbers for these three invariants. The first invariant is the trace of the stress tensor, sigma ii. The second invariant is half of the square of trace minus trace of a stress tensor square. And the third invariant is the determinant of the stress tensor. So we find these invariants. We solve this equation for sigma 1, 2, and 3, and having the principal stresses, we can solve the eigenvalue problem for three principal stress directions, three vectors for n. These directors are normals to principal stress planes. Then we can form a transformation matrix A star having these principal directors. The use of the transformation matrix A star on any coordinate system results in aligning that coordinate system with the principal directions of the stress tensor for that point. So basically you get a different stress tensor for each point, resulting in a different set of principal stresses and principal stress directions for that point, and transformation matrix specifically for that point. Here is an example. Given the stress tensor P, find the normal sigma n and shear tau n components on the plane at P with unit normal n. Then find the principal stress values sigma I and the principal stress directions nj of I, and also the transformation matrix A star. So let's start by finding the traction or a stress vector associated with the plane normal to n. It becomes from Cauchy's stress relation, Cauchy's stress equation, n dot sigma. The n vector, the sigma vector, and here's the result: 14.4, 4.2, and 0. That's the traction vector at that point, associated with the surface with normal n. Then the normal component sigma n becomes t dot n, which becomes 14.04 Pascal, and the shear component tau becomes t dot t minus sigma n square. Here is t dot t, and here is sigma n square, which becomes 5.28 Pascal. That's the solution for the first part. For the second part, first we need to find the invariants. The first invariant is the trace. The second invariant is half of trace square minus trace of sigma square. I've already calculated that. It becomes minus 225. The third invariant is the determinant of the stress tensor. I calculated that with MATLAB, minus 1125. Now let's form the characteristic equation for our eigenvalue problem. And again, I used MATLAB to find the three solutions for that equation. There we get sigma 1, the first principal stress, to become 15, the second one to be 5, and the third one to be minus 15. For the third part, to find the principal stress directors n, we need to solve the three unknown problem. This is the formulation: sigma ij minus sigma ji, delta I, sigma ij minus delta ij sigma multiplied by ni equal to 0. We replace sigma by 15, 5, and minus 15, and find Ni. Let's do it for sigma equal to 15 first. For I equal to 1, we get 9 minus 15 multiplied by n1 plus 12 n2 equal to 0. For I equal to 2, we get 12 n1 plus minus 9 minus 15 multiplied by n2 equal to 0. From both of these equations, you can find n1 is equal to 2 n2. For I equal to 3, we get 5 minus 15 n3 equal to 0, which gives us n equal to 0. So the first vector is any vector with n3 equal to 0 and n1 equal to n2. We set n2 to 1, so n1 is 2, and we divide it by 5 square root to normalize the vector. For sigma equal to 5, for I equal to 1, we get n minus 5 n1 plus 12 n2, which results in n1 equal to minus 3 n2. For I equal to 2, we have 12 n1 plus minus 9 minus 5 n2 equal to 0, which gives us 3 n1 equal to 7 n2. We cannot satisfy both of them at the same time, so both of them should be 0. And for the last equation, I equal to 3, we get 0 and 3 equal to 0. So any value for n3 satisfies this equation. So basically, n2, the second principal director, is a vector with any value for n3 and n1 equal to n2 equal to 0. We set the n3 to 1, so it becomes a unit vector. For sigma equal to minus 15, for I1 we have 9 plus 15 and 1 plus 12 and 2 gives us n2 equal to minus 2 and 1. For I2 we have 12 and 1 minus 9 plus 15 and 2 equal to 0, gives us the same result. For I3 we have 5 plus 15 and 3 equal to 0, so n3 should be 0. It says that the third principal vector is a vector with n3 equal to 0 and n2 equal to minus 2 and 1. We set n1 at any arbitrary value. We set it 1 here, so n2 is minus 2 and n3 is 0, and we divide the vector by 5 square root to normalize it. To find the transformation to the principal directions, A star, we basically put n1, n2, n3 side by side and then transpose the matrix, which gives us a 3 by 3 matrix of 2 over 5 square root, 1 over 5 square root 0, 0, 0, 1, and then 1 over 5 square root minus 2 over 5 square root 0. And that's the complete solution for part 3. Let's review some properties of principal stresses. Principal stress and stress invariance are real scalars, so they're not imaginary. If sigmas are distinct, the associated principal directions n of I are mutually orthogonal, meaning that if we dot product two of the principal directions, the result is 0. They can create an orthogonal basis. The transformation A star to principal direction coordinate frame is, as we've seen, A star is equal to n1, n2, n3, and then transposing the whole matrix. In the principal axis of reference, meaning that after rotating the system with A star, the principal stress tensor is diagonal with sigma 1 more than sigma 2 more than sigma 3. The stress invariance can be written in terms of principal stresses. That the trace is obvious for the first invariant. The second invariant is simplified to sigma 1, 2 plus sigma 2, 3 plus sigma 3, sigma 1. And the third invariant, the determinant, is simplified to sigma 1, sigma 2, sigma 3. And the transformation relating any arbitrary stress tensor to the principal stress tensor is sigma star, the principal stress tensor, equal to A star sigma A star transpose. It's basically the tensor transformation rule that we've already seen. You remember from last session that we talked about the infinitesimal strain tensor. Well, now it's not very strange to know that we can have principal strain and principal strain directions. Look here, we have the reference or undeformed cube. And with infinitesimal deformation, we have a not noticeable deformation in the deformed state. As said, similarly for epsilon, which is a symmetric second order tensor, we can have principal values epsilon and principal directions n. And also we can have invariants, first, second, and third invariants. The principal infinitesimal strain tensor becomes a diagonal tensor with sigma 1, sigma 2, with epsilon 1, epsilon 2, and epsilon 3 as the diagonal elements, and the invariants in terms of the principal strain values are these, basically similar to the case of a stress tensor. Finally, we have an example for you to work on during your break before we start the fourth part of this lecture. It says consider a planar infinitesimal strain case with epsilon 1, 1, gamma 1, 2, gamma 2, 1, and epsilon 2, 2. The rest of elements to be 0. Find the principal strains, epsilon 1 and epsilon 2. You have an eigenvalue problem to solve here. So basically you have to form the invariance first and then solve the eigenvalue the characteristic equation for the two roots epsilon 1 and epsilon 2.